organizers for inviting me, and thank you all for coming. So I'm going to talk about some joint work with Michael Landry and Yair Minsky. So I want to start with one way of motivating what we were thinking about. So I'll start with the Nielsen-Thurston classification. So let S be a closed orientable surface of genus at least 2. Then the classification says the following thing. Right? What it's going to do is it's going to give some geometric structure to an arbitrary homeomorphism of the surface. And what it says is if you take an infinite order element of the mapping class group, then either that element is going to fix the isotopy class of a collection of disjoint simple closed curves, or it's going to be isotopic to a pseudo-Anosov map. So we should think of this having this type of mapping class having sort of an optimal type of representative. And what does that representative do? Well, it's this picture that I stole from Dan Margalit. So I have this type of homeomorphism of the surface. It leaves invariant 2 foliations. So here, the one foliation is red, one foliation is blue. These are singular foliations on the surface. One foliation, its leaves get stretched by a constant factor, and the other foliation, its leaves get compressed by the reciprocal of that factor. Okay, so this is some kind of structure associated to a typical mapping class. Okay, so this is the classical setting, and the question that can motivate some of the things I'll talk about is what can be said when we're dealing with a more exotic type of surface. Okay, what can be said when we're dealing with a surface of infinite type? So of course, if I have a closed surface, it's compact, its fundamental group is finitely generated. An infinite type surface is one whose fundamental group is not finitely generated. Okay, this is some kind of motivation for what I wanted to talk about. This question is far, far too general. Typical infinite type surfaces can be quite hard to deal with. I'm going to focus in on a specific type of infinite type surface that will come up naturally when studying these pseudo-Anosov homeomorphisms. Okay, so how does one study these pseudo-Anosov homeomorphisms in the first place? So one often constructs their mapping torus. Okay, so let's fix one of these homeomorphisms, and I'm going to let M be its mapping torus. So you're probably used to seeing this picture. So I take the surface, I cross it with an interval, and I glue the top to the bottom using the homeomorphism. So maybe you're think about it in this upper left picture right here. I took my surface, I crossed it, I have a product now, and I simply glued the top to the bottom. Okay. The properties of this homeomorphism are going to be reflected in the properties of a certain flow on this manifold. And this is a flow we're going to use to understand the homeomorphism and the manifold itself. So in this structure, all I'm going to do is I think about the vertical flow, these vertical flow lines that go along the interval direction, right? And then they get glued up when I build the mapping torus. Okay? So this is the upper left is sort of the picture of just crossing it with an interval and gluing the top to the bottom. However, dynamically, the flow is much more complicated. So this is sort of a picture, this picture I stole from Michael Landry, of the global dynamics of the flow. So if kind of just remind you what was the structure of the pseudo-Anosov homeomorphism we started with. So we had the surface. That's my surface, my initial surface. It had these 2 transverse foliations, one of which is stretched, one of which is compressed. These 2 foliations suspend when I cross with the interval and glue the top to the bottom to two-dimensional foliations. Okay, and these are preserved under the flow. And in one of them, the flow lines are sort of expanded exponentially, and in the other one, the flow lines are contracted exponentially. This is just sort of capturing the dynamics of the suspension flow. I'll come back to this picture a couple of times throughout this talk. Okay, and then another way of saying what the structure is, I want to remark that S in this case is a fiber and a fibration of the manifold over the circle. Right, so writing our manifold as a mapping torus is a way of seeing it as a fiber and the fibration over the circle. Okay, so this is going from a pseudo-Anosov homeomorphism to its mapping torus with this flow. Okay, one kind of incredibly important feature of this picture is that the manifold we just constructed, can be written as a mapping torus in many different ways, fibers in many different ways. And one can understand sort of the picture of the flow and the pseudo-Anosov homeomorphisms by understanding the various ways this manifold can fiber over the circle. I want to give you one concrete way of attempting to think about that. Okay, so I'm going to look at the first cohomology of my manifold with real coefficients. That's a vector space. There's a cone in that vector space, an open cone in that vector space called a fibered cone. And I'm going to just describe it to you in a specific way. It's not the original description, but I think this is a nice way of thinking about it. So for any integer class in that cone, any incompressible surface representing a class in that cone, here I'm thinking about a surface representing a point in that cone using Poincare duality. This cone has the property that every such surface can be realized up to isotopy to be transverse to that flow and intersect every orbit infinitely often. Okay, so this cone, I'll say it again, this cone has the special property that every incompressible surface in the manifold whose homology class sits in that cone can be isotoped to intersect the flow transversely and infinitely often. Okay, so that's a fact you should believe. Okay? But now everything I also say is sort of trivial from that fact. So if your surface is transverse to the flow and intersects every orbit, then you get a well-defined first return map. Okay, what you do is you just add a point on your surface and you simply flow along this suspension flow we've already defined until you hit the surface again. Okay? And that defines a homeomorphism of the surface. And what it does is it realizes the manifold N that you're in as a mapping torus of this new surface with its first return map. Right? So this is just to say, if you have other transverse surfaces, other cross sections of this flow, then you could just see your manifold fibering over the circle in a different way. Another fact that is not so hard to see is that the first return map also has this pseudo-Anosov property. Why is that? Again, we're supposed to see it just by thinking about the picture. We have these two-dimensional foliations, right? And a transverse surface that cuts through those foliations. And the intersection are two foliations of the surface. And the dynamics of the flow are supposed to show us that one of them is expanded and one of them is contracted. Right? So these first return maps organize all these different pseudo-Anosov homeomorphisms. Okay, so what's the upshot here? It's like, well, this is one way of studying these pseudo-Anosov homeomorphisms that I'm sort of motivating the story by using all the properties of this flow, okay? And understanding how different ways the mapping tori fiber over the circle. Right, so that's one story. From this perspective, sort of any cross section to the flow, any surface that lies in the interior of this cone, gives you a way of representing the manifold as a mapping torus, gives you a way of representing the manifold comes with sort of this foliation by fibers. So a natural question to ask from this perspective is, well, what can you say about surfaces that are not in the interior of the cone, but just in the boundary of the cone? Okay. Sort of part of the talk is going to be, so I asked two questions so far, something about the boundary of the cone and something about infinite type surfaces. And so sort of the theme of the talk is sort of answering those two questions at once, which we'll see in the coming slides. Okay, so Thurston already tells you what you should think of what happens with the surface and the boundary of the cone. So right, in the interior of the cone, you get these foliation by fibers. It's a fibration of the free manifold. When you're in the boundary of the cone, you get a different type of foliation. Okay? You get a foliation where the components are exactly sigma. Okay? And then when you remove those compact leaves, what you're left with is a foliation again by fibers, like the complement of those compact leaves, fibers over the circle. Okay, so this is an example of what's called a depth 1 foliation. So why is it depth 1? The depth 0 leaves are the compact leaf sigma. Okay, and when you cut along those leaves, what you're left with is a manifold that again fibers over the circle. In this picture, this open manifold that fibers over the circle, the fibers are of course surfaces, but they're surfaces of infinite type.
So if I'm in the picture of two fiber faces, will I be a depth 1 foliation in like two different ways or something?
That surface will be a compact leaves of two different, very different depth 1 foliations. That's right. But we'll see in a second, given a surface sigma, there's lots of different depth 1 foliations associated to it. It's part of a bigger story.
How similar or different can the different foliations look when you're in the
Yeah, quite different. Yeah, I mean, they're all transverse to this flow that kind of unifies the story, but these are all foliations. These are all, fibers of different complexity, different stretch factors associated with the pseudo-Anosovs. Yeah, it's part of a big story. Okay, so Thurston thought about this. Okay, in one way. Let me give you an easy way of thinking about these foliations. Okay, you just have to kind of believe one fact. Okay, so this is a construction called spinning, and I might draw a couple of more details. Okay, so remember we have this surface sigma, okay, and a flow, and our fixed flow. That's just the suspension flow that I initially get by building my manifold when I didn't build my manifold. Okay, so first here's a fairly deep theorem of Lee-Mosher, but I just want you to believe it, that sigma itself pretty much can be realized transverse to the flow. So sigma is just this other surface. It could be realized up to isotopy also being transverse to the flow. Now, that's not quite true. First of all, Lee says you might have to re-choose sigma in its homology class, but that's not a big deal. It's of something I'll say later. And then there's an issue where you might need to modify the flow slightly. There's something called being almost transverse to the flow, but I don't want you to worry about that either. Yeah.
You say changing it with homology class.
Yeah.
Can you keep it in the same isotopic class?
So Lee's theorem says you might have to re-choose it within its homology class. We prove something stronger, and I might remark on it later, where any norm minimizing surface can be made transverse to the flow.
Was actually transverse to the flow, wouldn't it be a fiber?
It's transverse to the flow, but it misses orbits. It misses orbits. Yes, hopefully that was clear before. In order to define a first return map, you need to be transverse to the flow and intersect every orbit, infinitely often. So just being transverse, you might miss orbits, and there's not a well-defined first return map. So the answer to your questions, you can realize them in the isotopy class, but that's not Lee. That's more recent work. Okay.
The sigma is on the boundary.
The sigma's class is in the boundary of the curve. Yeah. Okay, but now there's this really simple thing you could do called spinning. Okay, so now let's redraw the picture right here. So here's my manifold. Here's sigma. So the flow is like vertical in this picture. Okay, and originally, let's take another fiber surface, S. So S is maybe my original fiber. Okay, it's a cross section to the flow. It intersects every orbit transversely and infinitely often. So there it is. Okay. So from this picture, you could produce lots of transverse surfaces just by doing like a cut and paste operation between S and sigma. Okay, so I delete the intersection and I smooth it in a way that maintains transversality to the flow. Okay. It's literally this operation if I cross it with a circle, right? That's locally what's happening. Is that cool? Okay. So that produces, okay, so in this picture, I just produced S plus sigma. That's how the homology class changes. Okay. And what I could do is I could just continue doing this operation. And if I carefully arrange in the manifold, I could do this operation infinitely many times. Okay. And what I do is I produce a new surface L. Okay. Notice each time I do this operation, I pick up genus. Right? I pick up some of the genus corresponding to sigma. So if I do this operation carefully infinitely many times, what I'll do is I'll get an infinite type surface L, a surface with infinite genus, that accumulates on the surface sigma, and that's the only place it accumulates. My operation went. What's nice though is, okay, so S and sigma were transverse to the flow. I can clearly do this so that my resulting spun surface is still transverse to the flow. Cool. So it's transverse to the flow, and it also intersects every flow line infinitely often, because I assume that about S. Okay, and then if you believed me before that if I have a surface and it's transverse to flow and it intersects orbits infinitely often, then you can realize your manifold as the mapping torus using the first return map. Okay, so just like that, I also have a first return map for this infinite type surface. And if you thought about it a little bit more, what is its mapping torus? Its mapping torus is the manifold minus sigma. Right? If you start at a point on L and you flow up, you'll sort of fill up all of the manifold, except you'll never quite get to sigma because of the infinite spinning of both above and below sigma. Okay. Now this is my foliation. So what's my foliation? My foliation is M minus sigma is foliated by parallel copies of L. It's a mapping torus. And I just throw back in sigma. And that's the foliation that Thurston was talking about. Okay, let me just zoom out a little bit and say, what did we just do? What did we just construct? Okay. So on this manifold, I get by cutting M along sigma, my surface. So I get a new manifold. So that's a manifold with two copies of sigma, two different boundary components. So this manifold has what I just referred to as a depth one foliation. So the depth 0 leaves are exactly the boundary leaves. The depth 1 leaves are these leaves that I constructed that are all parallel to L, these leaves that are spiraling into boundary plus and into boundary minus, and determine a fibration of n minus its boundary over the circle. And then what's left over is there's this semi-flow in this manifold that's transverse to L. So just summarizing, what did we produce? We produced this first return map on this infinite type surface, and we call this map a spun pseudo-Anosov map. Okay, why? We sort of got it by doing this spinning operation, starting with the pseudo-Anosov homeomorphism of our initial surface.
The monochrome, how is it related to the
Yeah, it's a good question. So a priori, there's not like an easy thing to say. So soon I'll define a stretch factor, and maybe the easiest thing to say, which I'll try to say later on, is there's somehow a core dynamical system inside of L, some compact invariant set, and that core dynamical system lies as like a sub-dynamical system of the pseudo-Anosov. But it's a somewhat complicated relationship. Okay, so these are the types of maps. So I don't know, spun pseudo-Anosov maps of these infinite type surfaces. So I said this before, right? Phi preserves these two foliations. It stretches along one and compresses along the other. And my surface L that I just constructed by spinning intersects those two foliations transversely. So this type of first return map, this type of spun pseudo-Anosov map, also has this property that I spoke about at the beginning, that there are these two transverse foliations, one of which is expanded and one of which is contracted along the map. Is that cool? This is just me summarizing it. So I have this infinite type surface. It's a special infinite type surface. It has only finitely many ends. Those are the ones that arise through this construction. But now you could just ask this question, right? It's like the Nielsen-Thurston question from the first slide, but restricted to this class of maps. If I have a homeomorphism of an infinite type surface L, when is it isotopic to one of these spun pseudo-Anosov maps, the maps with the structure of the two foliations, with the expanding, contracting dynamics? So there's two basic topological abstractions. Yeah.
Expanding and contracting dynamics. Where you define
Spun pseudo-Anosov map, I specifically mean it is the return map of a pseudo-Anosov flow. Yes.
So it has to be a depth one foliation.
There has to be a depth one foliation, transverse.
Like surface and fiber.
There's a transverse depth one foliation.
Okay,
it doesn't necessarily need to come from my spinning construction. But it turns out that if it does for a different manifold, there's some kind of construction.
That's a good question. I keep on having this picture in my head that you're basically composing this pseudo-Anosov with a Dane twist. How is that the wrong picture? Because it's like when you're spinning it.
No. I mean, so if I did this once, you'd get a pseudo-Anosov map on a totally different surface. And they're related because they're both first return maps to a given flow. But if I just gave you these two pseudo-Anosovs on different surfaces and told you how are they related, you wouldn't see that in any kind of obvious way. I mean, there's this way in which they're related, but that's that.
In that picture, the horizontal thing is a surface, not a curve on a surface. So you're not getting twisted, you're shifting the surface by some number.
Yeah. This is just a schematic picture. Sorry about that. Yeah.
See how to draw, if we redraw n minus the boundary that's fibered over S1.
Yeah.
How do you see the finite contact surface in the boundary?
Yeah, there's a way. So Actually, I'll tell you I'll tell you now. Sorry for so much flipping. It has to do with one of these two basic topological obstructions to a surface being isotopic to one of these maps. Okay, so first of all, I have a homeomorphism of a surface, any surface. I'll call it atoroidal if it fixes no finite multi-curve up to isotopy, right? So there's no collection of curves that get mapped back to themselves up to isotopy. Okay? That's like a clear obstruction because my manifold I built is a hyperbolic manifold. And so there can't be invariant multi-curves because they would give me essential tori. Okay? So this is one obstruction, being atoroidal. It's the same as the classical Nielsen-Thurston obstruction. The other one is also topological, and I think this goes to answer Jonah's question. This homeomorphism, this first turn map, is called Endperiodic. The point is, if we look at the spiraling picture, we could see specifically what's happening on the ends of the surface. Right, the ends of the surface, the ends of L, are spiraling about sigma, right? And so if I looked at the first return map, it sort of just pushes me one level up in that spiraling staircase. Okay? And the same thing if I'm looking downward from the leaves that are spiraling from above. Okay? So in terms of the homeomorphism itself, it has this property of being n-periodic, which means each end of L is periodic and either attracting or repelling. So here's just a quick definition of what it means to be attracting. It means there's a neighborhood of that end, right? So under some power, it's taken back into itself, right? And then if I keep iterating, the intersections of those images of the ends is trivial. They form a neighborhood basis of the end. Cool. And then a repelling end is just the attracting end for the inverse homeomorphism. So to answer your question, just from understanding the mapping torus of an n-periodic map, if you go out a positive end, you sort of see the action of F looking like a deck transformation. Okay, and the quotient under that deck transformation is that positive surface at infinity. It's actually like a semi-cover of your surface. Okay, and now I'm just recording this fact that I wanted to say is sort of just comes from the construction that any spun pseudo-Anosov map has these properties. It's n-periodic and it's atoroidal. So atoroidal, just from the fact that the manifold's hyperbolic, n-periodic is the monodromy of any depth one leaf of a depth one foliation has this n-periodic behavior, because that's how the spiraling works. Okay, so here's the theorem that these two sort of obvious obstructions are the only obstruction. So every n-periodic atoroidal map is isotopic to a spun pseudo-Anosov representative. So let me unpack this for you. Okay, so just start with your map G and build its mapping torus. Okay, and what I could do is compactify it in the way I just said. You could compactify it by throwing surfaces at infinity that are sort of the limits of the spiraling. So what does the theorem really say? The theorem really says that there's actually exists somewhere else out there in the world a closed fiber 3 manifold with a pseudo-Anosov suspension flow, such that I could take my mapping torus n and embed it in that manifold so that the boundary of n and this infinite type surface L are transverse to the flow on my closed manifold. Okay? And when I do that, I get a first return map that's just, from topology is isotopic to the original map G. And it's the first return map of one of these pseudo-Anosov flows. Right? So in particular, the return map is one of these spun pseudo-Anosov maps. Okay, so this is just me drawing a picture of sort of completing the manifold n by gluing it to something else that produces a closed manifold with a pseudo-Anosov flow. Anyway, and then I just said sort of one of the main difficulty of the proof is an improvement of Mosher's transverse surface theorem to say when are surfaces transverse to the flow. Then there's a particular construction.
So the simplest one would be when you just kind of glue those two and limit things together. And then
So if I just glue them by the identity, if I double the manifold, it does not work.
Okay.
It does not work. That will produce a depth one foliation, but it won't be a fibered manifold, and there won't be a transverse flow. One needs to do something slightly more elaborate to produce a manifold that fibers over the circle, and for which the flow is transverse to the boundary then. Okay. Okay, so yeah.
You're manufacturing some finite thing out of your Endperiodic.
That's right.
So where is that hidden? Probably said it.
Where is it? Where is what?
Where is the, in the monogram? There
So-
is some periodicity which should allow you to extract out from the monogram of this infinite type surface, some finite subsurface which captures the action at infinity.
Yeah. So you have these ends of your surface that are mapping into themselves, right? So the interesting dynamics is happening in some compact subsurface, but it's not an invariant subsurface. It's not an invariant surface.
Think of that as a shift coupled with the pseudo-Anosov support.
Well, certainly one can build these maps easily by doing a construction like that, where you take a huge subsurface, you take a huge power of a pseudo-Anosov on that subsurface, and you can compose with some sort of translation of the surface. That's a way of constructing such maps. Yeah. And that's a good model to have in your mind of what these things can look like. Okay, so it's not lost on me that this is kind of out of the theme of this workshop, right? So where's the group thing? So, this is the talk I wanted to give, and so that's the talk you're hearing. But it did get me thinking a little bit. So here's just next couple of slides are just, I don't know, my thoughts. So of course, in general, everything I'm talking about are fibered manifolds, right? Even if coming to me in some form. So any fibration over the circle determines an exact sequence, right? Like this. And the classical picture, the picture we started with, is where S is a finite type surface. We started with the case of S being a closed surface, right? And so this is an example. I mean, it's kind of funny to say this, but this is an example of an algebraic fibering, right? So M for me is always compact. Every manifold, every 3 manifold in this story is compact. So I have a map to Z, and in this case, there's of course finitely generated kernel when S is closed. And that's what it means to be an algebraic fibering. And that's like a major theme of this workshop, right? Lots of people here are going to be discussing or talking about stories that sort of feed into this. And this is maybe like the first interesting, surprising, example of groups doing this. And there's actually more rigidity than that, right? Stallings proves that for any one of these compact 3 manifolds, maybe irreducible, any homomorphism to Z with finitely generated kernel comes from this picture. Right, it comes from a fibration over the circle. Okay, so here's just like the most naive question: can you say anything? What can be said group theoretically for fibrations over the circle where the surface has infinite type? Is there some kind of group theoretic interpretation of a depth 1 foliation? So I have no idea. Okay, but there are some I could ask a more specific question. So let me ask a more specific question. Okay, so suppose we have a compact 3 manifold N, and maybe the boundary then is not empty. And I have a map to a homomorphism to Z, and I'll call its kernel K, and I'll call its monogermy psi. Right, so psi here is just the the automorphism that comes from the semi-direct product structure with my map to Z. Okay. So is there any sort of infinite type Stallings like theorem, right? So what conditions on K or psi imply that this homomorphism to Z is dual to a depth 1 foliation. Right, so a depth 1 foliation of the manifold gives you a map to Z, as we just saw. In particular, when can my monogermy map psi be induced by an Endperiodic map? Okay. I don't know, just some thoughts about sort of the structure that B should have. Left ordering. That would be interesting. Maybe you could tell me your thoughts later.
Yeah.
Cool. So, okay, let me just tell you the most easy picture to keep in mind. Okay. It's the case of surface compact. So S is always a closed surface in this story. So every homomorphism to Z of the fundamental group of a closed surface is represented by a depth 1 foliation on surface cross I. Okay. So that's not so hard to see. So any homomorphism to Z, let's take one that's dual to a simple closed curve on S. Okay. Then in surface cross I, that simple closed curve, induces a product annulus. Okay? And I could tilt that product annulus slightly to be transverse to the vertical direction. And now I just spin my annulus around the boundary plus and boundary minus. Okay? And that produces a leaf of a depth 1 foliation where the monodromy is whatever homomorphism the Z I start with. Okay. So I said that quickly, but you could draw pictures and convince yourself that's the case. So in that case, you do get a depth one foliation for every cohomology class. And what's the monodromy? The monodromy is really simple. So here's my infinite type surface. Just an example of what it might look like on a closed surface. And in this case, the monodromy is just the shift map. The Endperiodic map is just, I don't know, the one you see, right? The one you grab a handle and just move it some number of units to the right. Okay. Yeah, maybe that's also an interesting exercise to convince yourself that you start with that surface. It's sometimes called the ladder surface, and you do the homeomorphism that we're all thinking of, where you just shift one genus to the right, and think about what the mapping torus of that is. Right? So that mapping torus, you could compactify it by adding the fundamental domain of that action to the top and the bottom, and the result there is surface cross. And I don't know, I call this is like a building block because I think any sort of, I don't know, this is too much speculation here, but any type of n-periodic map, one should think about is starting with this n-periodic map, whose mapping torus is essentially surface cross I, and doing some sort of perturbation on some compact subsurface, then doing some perturbation on some finitely generated, Okay, so before I end this sort of side story to the talk, I want, you might ask, well, why would you want this, right? You have this story of a three manifold with a depth one foliation. Why would you want an interpretation in terms of the group theory? Well, it's because there's a really similar story for depth one foliations, or what you could call depth one foliations of free bicyclic groups. So this is a similar structure that was discovered by Ruth Meadow McLeod. So I'm not going to do this justice, but if you have questions, she's here and you could ask her. Okay, so what's the similar structure? So now I'm looking at a free bicyclic group, and of course, a free bicyclic group is the fundamental group of the mapping torus of a graph. Okay, and I want to start with something that's like a pseudo-Anosov homeomorphism. So I'll start with a fully irreducible automorphism and a train track representative of it. So there were some mini courses earlier last week that sort of describe some of the structure. Okay, so now I have my train track map. My train track is called G. My train track map is capital F. I'm using the same notation as before because you'd think of it as the same thing. That's how it should be thought of. And now my mapping torus, so I changed notation. My mapping torus is now XF. Okay, so first part of the story is that Dowdall, Kapovich, and Leininger showed that there's essentially a fibered cone theory. There's this beautiful analog of understanding the various ways that your free bicyclic group can split as a semidirect product in a totally analogous way to understanding how a three manifold fibers over the circle. This is part of a longer story, but one thing they produce is one of these fibered cones where the classes in the cone are represented by these cross sections of what is now a semiflow. So this is going to Ruth's work. So similar to the story we just talked about, classes in the boundary of that cone can be represented by transverse graphs, that are not cross sections, transverse graphs that miss some orbits. But once you have this picture in the mapping torus, you could do exactly the same spinning construction. It's even easier to understand spinning a graph along another graph inside of a two complex, where everything's transverse to a vertical flow. And what do you get out of this? You produce L, which in this case is an infinite type graph, just meaning an infinite graph, with a first return map that's an n-periodic train track map. Yeah. It's a semiflow. Right, so the return map's a train track map. The return map is not a homeomorphism. It's a holding map. Yeah. Okay. So I realize I went through this really quickly. I'm just trying to, there's a similar story there. There's a totally analogous story for free bicyclic groups where one produces, in this case, what are these n-periodic train track maps? And as before, sort of the mapping torus of this n-periodic train track map is some subcomplex of your mapping torus. Okay. So the rest of the talk is going to be the last 10 minutes is sort of some of the structure of these maps. Okay, so I guess I spoke a lot about producing these spun pseudo-Anosov maps, and here's sort of a very quick description of producing an analog for free bicyclic groups. So in the remaining amount of time, I just want to tell you maybe why you might think they're interesting. Okay. So dynamical properties. Yeah, this is just this question. What's special about them? Why might you be interested? Okay. So for any map, I could produce what I'm going to call its growth rate. Okay. So what is the growth rate? I'm just going to look at fixed points of powers. I'm going to count the number of fixed points of powers and consider its exponential growth rate. So here, fix gn is just, I'll take the point set of the nth power of g. Okay. So the following theorem, again, this is joint with Landry and Minsky, is a description of what the growth rates are, we'll call stretch factors, of these spun pseudo-Anosov maps. Okay. And the point is to try to get a theory that mimics the theory of pseudo-Anosov homeomorphisms. That's like the point. Okay, so the first thing is that these spun pseudo-Anosov maps are essentially dynamically optimal in their homotopy class. Okay. So for any other n-periodic map that's homotopic to my spun pseudo-Anosov map, the stretch factor of the spun pseudo-Anosov map is minimal. So by dynamically optimal, I mean has the fewest number of periodic points. Okay. Right, you can imagine lots of isotoping your map in crazy ways, and what you'll do is you'll only produce more periodic points of the return map. Okay, so that's one characterization. Another one is a topological characterization, analogous to understanding these growth rates as stretch factors on the surface. If I were to take two simple closed curves on L, I could iterate one of them under the map and count the intersection, the growth rate of intersection numbers. Okay. That typically will grow exponentially, and so I'll look at the exponential growth rate of that. And again, I get the same quantity, this stretch factor. And third is that these n-periodic maps, it's not too difficult to see, have a unique, compact, invariant subspace. Okay. And the growth rate is, well, I should say the topological entropy of the restriction to that subspace, this compact subspace, is log of the growth rate. So these are all analogs of how one studies the stretch factor for a pseudo-Anosov map. So we'll call these numbers, these growth rates, the stretch factors of these spun pseudo-Anosov maps. Okay. And if you're interested, there's an analogous story again in the free bicyclic group, understanding stretch factors in the same sort of way. Okay. So maybe just I'll tell you a little bit about how this works. So the first part was that these spun pseudo-Anosov maps are have the tightest dynamics, the fewest fixed points. So here's the proof. Okay. What does one need to do to prove that the spun pseudo-Anosov map has the fewest number of periodic points among all n-periodic homotopic maps? Okay, so here's what you should do. You should imagine there's a fixed point of a power of my map. Okay, so I'll lift that point to the universal cover, and I'll lift a representative of my power to fix that point. Okay, so that's my picture over here. So I'm just lifting everything to the universal cover, and I'll choose the representative. I'll choose the lift to fix my point. So if this was any point lies in at least two leaves. One leaf lies in two leaves. One leaf of this expanded foliation and one leaf of this contracted foliation. Right, that was part of the structure I started with. Those leaves, one needs to prove this, but those leaves determine well-defined points on the circle at infinity. Right, so the surface is still a hyperbolic surface, the universal cover is still the hyperbolic plane, and those leaves terminate on endpoints at infinity. And what one needs to show is that those are actually sources and sinks for the action at infinity. Right, so this is indeed the case, right? If this is the expanded foliation, this is the contracted foliation, right? Then you have the sort of synced source dynamics that one would expect at infinity. So why is that useful? Well, that action at infinity depends only on the homotopy class of the map. Okay, just like in the finite type setting. So what one has is for any homotopic N-periodic map, one sees the same dynamics at infinity, right? But now you need to do is use some sort of fixed point argument to say that if you see this kind of dynamics at infinity, then any homeomorphism of the disk that induces it at infinity has to have a fixed point in the interior. So in this way, one transfers fixed points of his spun pseudo-Anosov representative to fixed points of an arbitrary N-periodic map. So here, what the work is all producing is to produce that you have the right picture at infinity and the right dynamics on it. Okay. For this one, what one needs to do is to understand, how two curves under iteration intersect one another. And what one does, there's various ways of proving this for closed surfaces, but one way of doing it is to understand a train track representative. And indeed, part of the structure that comes from these spun pseudo-Anosov maps, one can use a structure of M called veering triangulations to produce canonical train track representatives of these maps. And once one has these canonical train track representatives, then morally one's dealing with like an infinite dimensional transition matrix for this train track. But because of the N-periodic nature, most of what's happening is junk, and one can focus on some finite transition matrix whose spectral radius is the growth rate, just like in the finite type setting. Okay, and then maybe the last slide is to just say what's this, topological entropy statement about. Well, you have this infinite surface, okay, and this homeomorphism of the infinite surface. One can simply collect the points whose orbits are bounded. Right. So if I'm in a sort of the far out in the positive end of the surface, then by construction, when I positively iterate, I escape the surface. Okay. But there could be some points such that under iteration, they stay in some compact part of the surface. So this is a compact invariant set. And this is the set for which the topological entropy of my map restricted to the set is log of the stretch factor. So the proof of this is maybe addresses one of the first questions that I got. So what's the relationship between the spun pseudo-Anosov surface I got, and the pseudo-Anosov on the cross section I started with? Okay. So what the proof shows is that this compact invariant set can be isotoped along the flow, basically flowed back into my original surface, where in that original surface, it's invariant for its original pseudo-Anosov map. Okay, so this core dynamical system occurs as a subsystem of an actual pseudo-Anosov homeomorphism. And then a little bit more work shows that implies that F restricted to this core dynamical system is coded by a subshift of finite type. And then it's just standard dynamics to say that the topological entropy is recorded by the exponential growth rate of periodic points. Okay. I still have 10 minutes. Okay. Yeah, I'll take a few more minutes. Yeah, so yeah. It was this one.
Yeah. Now, homotopy or proper homotopy?
So G is also N-periodic. That any homotopy works. The difficulty here is what I didn't say is it's easy to see that these are sinks and sources for the action on the circle at infinity. One actually needs to say that they're sinks and sources for the action on the disk. And maybe that's what's.
That's what I was writing about. Said the homotopy thing was at the same action as infinity, but I felt like.
That's true because the ends. No, that's true just in general because the ends are non-planar. The ends are non-planar by construction. So there's every map is realized by like a proper homeomorphism, isomorphism. We can talk about it. Yeah. Okay, so maybe I'll just end by saying something about a connection with a previous way of how one studies these N-periodic maps. So there was work done in the late 80s, early 90s by Handel and Miller to understand N-periodic maps arising because they arise as monodromies of depth one foliations. So really, this is only recently completely written up in work of Cantwell, Conlon, and Fenley. So I'm going to say this very informally. What it is it's basically a lamination theory, right? The way one generalizes sort of the Casson-Bleiler approach to understand pseudo-Anosov homeomorphisms, one understands invariant laminations. Okay, so just concluding for people who are maybe aware of this theory is that these spun pseudo-Anosov maps are examples of these Handel-Miller laminations, Handel-Miller maps. And maybe something to say that's maybe slightly easier to understand is this previous theory gives you laminations that are invariant under the maps. These laminations actually naturally arise as sublaminations of these invariant foliations. Right? So our theory gives you these invariant foliations that naturally come from the stable and unstable foliations of the initial pseudo-Anosov, of the pseudo-Anosov flow. And if one takes those foliations and throws away leaves that sort of venture into the wrong ends, what one is left with are singular laminations that are these canonical Handel-Miller laminations. So an expanding lamination, right, is everywhere on the surface, right? The laminations fill the surface. So there are leaves of the expanding lamination that are in pieces that go to negative infinity under negative iteration. One throws away the leaves of those laminations. One throws away those leaves. And what's left over turns out to be closed and foliated. It's an invariant sublamination. And those are the correct laminations to study from this alternative theory. Okay, so the upshot here is just that this previous theory that studied Endperiodic maps can be realized as sort of a shadow of this classical setting, which is pseudo-Anosov flows on closed three manifolds. Sort of that setup, these types of flows on these manifolds see the entire theory of Endperiodic maps. Now I'll end there. Thank you. So these manifolds are all hyperbolic manifolds. They're all, what should I say? So they're all, irreducible atoroidal manifolds. So they have, I'm missing an adjective there, irreducible, atoroidal, compressible boundary. So they all have admit manifolds, admit hyperbolic metrics on their interior. If you additionally assume that there are no invariant curves and no invariant lines under the map, what one could also establish is that the manifolds are acylindrical. And so there's like a unique best hyperbolic metric, the one with totally geodesic boundary. And I think it's like a beautiful question, like how could one understand the geometry of those manifolds using properties of the Endperiodic map? So properties of the Endperiodic map should tell you something about, for instance, the volume of these manifolds or the short curves of those manifolds. And those are areas of active study, understanding the geometry of the mapping tori, these particular types of mapping tori, using properties of the Endperiodic homeomorphisms. Higher depth foliations. Yeah, I mean, I don't know. Why not? Why can't there be a?
We should limit to have two compact pieces and power.
Well, yeah, depth. If there's a depth two foliation, the depth two leaves would limit onto the depth one leaves. I mean, I think that's a question that hasn't been studied. Can you produce you can produce them, but what degree of flexibility do you have? If you start with a more general type of map of infinite type surface, you consider its mapping torus and try to compactify it in a way such that that initial surface is a highest depth leaf of a finite depth foliation, and then when could that be made transverse to a pseudo-Anosov flow? I think of these all as like structure theorems, right? I start with just a homeomorphism of a surface, and then I want to realize some kind of geometry associated to it, like these two foliations. And I think that's a good question, but I don't know the answer.
Yeah, so you had a picture where you kind of filled it in with some blob. So it doesn't, you told me it doesn't always work just to glue it together.
Oh, sorry. Yeah. Should I go back to
that?
No, here?
Yeah.
No, so no, the construction's not so hard. So I take two copies of N, and what I do is I'm going to glue their boundaries together in a way that I could like match the cohomology classes. So on the other copy of N, I also have L spiraling, the other copy of L spiraling, and I want to glue them in such a way that I could sort of take pieces of the spiraling and connect them across N in a co-oriented way. And if I can do that, maintaining some kind of transversality to the flow, then I produce a fiber in of a foliation of my new surface.
So it's like if it had totally geodesic boundary, it'd be like doubling the.
If it was totally geodesic boundary, like you could just take the hyperelliptic involution on each component and that would work. I need to reverse the cohomology class. Yeah. The hard part is when I do that, I just produce sort of junk. The flow is junk, and I need to replace that junk with the honest pseudo-Anosov flow. And when I do that, the question is, well, then how do I know my boundary n is still transverse to that? And that's what this